How's everybody doing today?
Good. Doing well.
Good. Okay, so where did we leave off? Well, we were about to discretize our problem. We're working on this finite element method that's kind of built with splines in mind. So let's see. Yeah, so what we want to do, let's go ahead and refresh our memory on a few things. Well, maybe before we dive in, is there any questions on anything?
I have a question, Mike, but I have to double check the notes to remember what it was. It came up when I was reading them.
Okay. Did have one comment I wanted to make about to the people taking the class. There is a FERPA sheet. Go on the Learning Suite. Let's see. Let me share my screen here. Okay, so there is an assignment called Submit FERPA Form. And these, I need to have the BYU students either sign it or decline to sign it so that we can either, because I want to put these up on YouTube. And so I need to get permission from students who may appear in the videos or their voices or whatever, that's okay. So let's see how many BYU students I have on here. I think most of them are here. So let's, so can you guys just hop on to Learning Suite right now and let me know what you're gonna do there so that I can finish posting these videos. Okay, great. Let's go back to whiteboard here. All right, so we've got the following. Let's write down our Galerkin approximation because that's going to be our starting point today. So it is the following. Let's call it d pi. Can you guys see my screen okay?
Yes.
Yep. Yep.
Okay. It's going to be mostly derivations today, so please stop me if you have any questions. So this is the Galerkin form I'm going to write down to refresh our memory. So we have an integral over the domain 0 to L. It's our bar. Delta U H comma X, derivative. EA U H comma X dx plus delta UH at 0 lambda H minus 0 to L delta UHF dx minus delta UHL H sub L equals 0 for all delta UH. And we'll call it VH.
Could we have a quick reminder where this is coming from?
Yeah, let me write down the other one and then I'll go through it.
Yeah, and as you do that, Mike, can you just concisely remind us what each term is? For instance, this is the integral, surface integral of your traction. This is the body force, etc.
Yep, I will. Let me just finish. This is a short one here. I just want to write it down. Delta lambda H Let's see, U 0 minus U naught. Okay, so if you remember, we've got our bar. We have this bar here. Zero to L. This term here is the strain energy, or not the strain energy, but yeah, I guess you could call this strain energy, but it's let's write a few things down here. If you recall that stress in 1D, Young's modulus times strain, which is equal to E U comma X. So what we have up here is essentially the variation of the strain times the stress, and then just scaled by cross-sectional area factor. So this is stress times strain in here, right? So this is like the kind of like the work done by the strain. Then what we're doing with the Lagrange multiplier is we're enforcing at the left end, we're going to enforce some constraint U naught. We're going to enforce a displacement constraint at x equal to 0. And then we're going to apply a traction H sub L on the right end. And then we're going to apply a body force F throughout the length of the bar. Okay, so this is the term that comes from enforcing the constraint on the left end. This is the work done by the body force. This is the work done by the traction. This is the work done by the Lagrange multiplier, or the force required to enforce the displacement constraint. Work done by the body force, work done by the traction. And we're saying that we need equilibrium, so that whole thing has to be equal to 0 for every possible variation in the displacement. And then here we have, again, a work term that's enforcing the displacement constraint, that the displacement at 0 has to be equal to U naught. So that's every term. It's just equilibrium. And it's just an equilibrium statement. And that's what we call our Galerkin form, comes from our weak form. Did that answer your questions on what everything is?
Yes, thank you.
Okay, now let's go ahead and discretize. So we're going to introduce a basis, as I described, a spline basis over this flex domain, right, where we essentially create a larger domain that encapsulates the domain that we're actually solving the problem over. We build a basis over that. And now our delta, let's call it delta U hat H, is a function from the parametric flex domain into the reals. And it's going to be equal to nothing more than a linear combination of coefficients times the basis that we talked about constructing over the last two periods. So this will be our, this here is omega F, this here is omega C, and then let's call this omega hat F, and then there's going to be a mapping that takes us from omega hat F into omega F. Okay, so we can write our variations in displacement in the parametric space as a linear combination of unknown coefficients times our basis functions. We can also write our displacement field that we're going to be solving for in the parametric domain as, again, linear combination of our basis. And now what we're going to do is, remember, we're not solving our problem over the parametric domain, we're solving it over the physical domain. So we're going to actually write our final values that we're going to plug into our Galerkin form as delta U hat H composed with the inverse of our mapping, which then can simply be written as CA NAF, and UH similarly as U hat H composed with the mapping minus 1 is equal to dB and BF. Okay, so now what's happened is we've taken our basis functions that were originally defined in the parametric domain and we've mapped them up onto our physical domain. And we're going to use these functions to approximate our solution. And so that's what this mapping is, right? It takes something that's defined in the parametric coordinates and makes it defined in terms of the physical coordinates. This is very classical. It's nothing more than what we call an isoparametric mapping. It's what, you know, very standard practice that is done commonly in structural finite elements. Okay, now what we can do is we can take these expressions here and written in terms of our basis. This is like our culminating moment here. And we can take them, and everywhere you see a UH or a delta UH, we plug in those guys. I had like a bigger whiteboard here. So let me erase this. And okay, now let's talk about our Lagrange multiplier. We also need to discretize our Lagrange multiplier. Okay, so to discretize our Lagrange multiplier, we have that delta lambda h. Remember, it's just a number. It's just a single value. We just have 1 degree of freedom that we're solving for. So we're going to write it delta lambda n plus 1 times n plus 1. And lambda h is lambda n plus 1, n of n plus 1, where in this case, n, remember we have n normal basis functions, and then I'm saying let's add 1 additional basis function to model our Lagrange multiplier, but since it's a single number, let's set it equal to the constant 1. So n plus 1 is just the value 1, and so we're just basically solving for the coefficient directly. But it's good to recognize this form, because when we move to multi-dimensions, then again, it won't just be a number, it'll be a function. All right, guys, so let's go ahead and plug everything in.
Dr. Scott, could you explain one more time why we need to add another basis function to model the Lagrange multiplier?
Yeah, because we're using so we have this basis, right, that we talked about. we're calling these NF. So we have like N1 through N of these guys. We're using these guys to create what we call for our displacements, the space where we're looking for our displacements, right? Remember, we're looking for our displacements in a space, and then we're going to look for our Lagrange multipliers in another space. And so we actually need a basis function for our Lagrange. Maybe we'll call this LH for our Lagrange multipliers. But in this case, we have our bar in here, right? And we're enforcing that u at 0 is equal to u naught with a Lagrange multiplier. But since it's just at a point, the Lagrange multiplier is just a number. We're just going to solve for the value of the force. So because that's just a constant, the only basis function I need is a single basis function that's equal to a constant.
Yeah,
So
thank you.
That's what we're doing. But in general, let's say you have a domain like a multi-dimensional domain, and let's say you wanted to enforce a constraint on this entire boundary. Then what you're going to do is actually build another basis. You'll have your basis on the interior, and then we'll have some basis functions that live on the edge. And then these will actually form a space LH. In this case, it's so trivial that it's just the space of constant. It's just the real numbers. It's just the constant values. So it's not necessary. But I like to keep this notation so that you don't forget what's coming. Okay. All right, so let me erase this and let's plug everything in. Let's see what pops out here. All right, so we're going to end up with these equations. So sum on B of integral omega f chi c x a comma x dB plus n a 0 f and n plus 1 plus 1. That whole thing is equal to our applied forces, which is F chi x. And so there's our first set of equations. And then the equations that come from the Lagrange multiplier are B Okay, so where does this come from? Well, all we did was everywhere you see delta UH or lambda H or delta lambda H, we plugged in the linear combinations and simply rearranged the sums. So I'd encourage you to go through in fact, I think I require you to go through the algebra there to make sure that you can do that. And then you get these equations. So let's talk a little bit about them. Okay. So notice what I've done. I have replaced everywhere that you have an integral over the CAD domain. What I've done is I've approximated that integral with an integral over the flex domain, where I have what's called an indicator function, where this indicator function is equal to 1 if the point is in the CAD domain, or some small value epsilon if it's not in the CAD domain. So I've replaced integrals over the actual CAD domain with integrals over the flex domain, and I'm using an indicator function to determine which points are inside or outside the CAD domain. Why do you think I'm doing this, for example? What is the advantage of doing something like this? Any thoughts?
It's a weighting function.
So the indicator function is not a weighting function. I mean, I guess it's not a weighting function in the sense of coming from a function space. It is performing a weighting of sorts, but why are we doing it?
To scale the space outside of your domain to 0?
Yeah, so basically what it says is if my CAD domain is this guy, and it could be arbitrarily complicated, well, I could create a simpler flex domain. And as long as my CAD domain lives in the flex domain, this domain is really simple, omega f. And the way that I approximate my geometry now is simply through a test on every point in the domain, whether it's inside or outside. So as I go through here and look at all the points, then what's going to happen is, only the points on the inside will contribute to the energy of the system. And this is significant because now I don't have to come up with a way of building a really complicated mesh over my CAD object. I can always kind of cop out for a simpler domain, omega f. And then as long as my spline functions that I define of over omega f can accurately represent omega c in the context of these integrals, then I've really dramatically simplified the problem. And this works really well with higher order splines because of their intrinsic properties. And so that's why I say we're really building methods with some foresight into the fact that we're going to be using splines. Okay, any comments or questions on this? This is kind of a big thing here, a big deal.
You mentioned,
Go ahead.
you mentioned that epsilon was supposed to be arbitrarily small. Why can't we just make it 0?
So theoretically, right, if epsilon was 0, that would be nice because then I could remove this approximation and it would be an equality, right?
Right.
But what ends up happening is if you drive epsilon to 0, the discrete linear systems become very poorly conditioned. And so in practice, what we do is we set some epsilon value close to machine precision 0. And
Okay.
what it does is it regularizes the problem. So it's basically a numerical, this is essentially a penalty. Epsilon is kind of like a penalty where we're penalizing all of the domain that's inside of omega C and trying to like throw away everything else.
Okay. And so is epsilon ever like algorithmically defined, or is we just arbitrarily like hard coded in
Yeah,
and
it just
say,
has to be something small. Like usually people choose somewhere like 10 to the minus 8 to the minus 12, somewhere in that range.
okay.
And it just regularizes the problem slightly, makes it a little smoother and easier to solve.
Mike, can
Yeah.
you comment on the limiting case of doing it this way versus a conformal mesh in terms of your error?
Well, in asymptotically, this is a Galerkin method. You're going to converge to the exact solution. Like there will be no difference between, if you have an infinite number of basis functions, there will be no difference between this method and a body fitted method.
Sure, but in practice, we're rarely even in that asymptotic regime, right?
So in practice, you're going to engender, if you were to use like linear basis functions, you would engender quite a bit of error along these boundaries. But what we find with splines is that error is far superior to what you would achieve even with body fitted traditional FEA. And in fact, it converges, all of the boundary quantities converge optimally. At higher order rates, all of the quantities converge optimally on the boundary.
Is that just for one dimension, or is that true in?
Yeah, it's true in multiple dimensions. Yep.
So how do you evaluate your functions outside of omega C?
Well, remember, omega F is the domain that we construct.
Mm-hmm.
So omega F is just, you pick what that domain is and you construct your basis functions over it. And then what you actually do is you're going to integrate, we'll get to this in a minute, you're going to integrate omega F, not omega C. And every point you just run through this indicator function here.
So I guess what I mean, so the integral that you have at the bottom there, you're like just integrating, you're calculating the area of the omega C. What if you're trying to integrate a function over the domain, but that function was only defined on omega C to begin with? So what do you use as the definition of that function outside of it?
Yeah, in fact, we do it right here. Like, let's look at this guy right here. Right, because here's our body force. It's defined over the geometry, right? The CAD geometry. So it's a function of X. So all you do is you integrate. What we're going to do is we're going to do a change of variables. We're going to pull this, I'll do this in a minute. We'll pull this back to the parametric flex domain. And then what you'll do is let me pull this out a little bit so I have a little more room. This will become F X F of XC. And then you just have, so this F is defined over this domain.
Mm-hmm.
In terms of physical coordinates. So you map your parametric coordinate into physical coordinates, as long as, and then you test and you say, am I in the CAD geometry? And then if so, you simply evaluate your function at that physical coordinate.
And if you're not?
If you're not, you don't do anything, right? You don't do anything with it.
Okay.
Or you can set it to some arbitrarily, it doesn't really matter, right?
Mm-hmm.
At this point, when you're outside and this evaluates to some small number,
Mm-hmm.
the actual values of these functions no longer are relevant. It's just a small value that you're using to regularize your system.
I see.
It's essentially like saying, here I have steel, and then out here I have jello. You know what I mean? Like, it's like this has no stiffness out here. But there is still this, we call this, a term that's often used is the fictitious domain. It's still there, and we use it numerically to regularize the problem, but it doesn't disrupt convergence or accuracy or anything like that.
Okay, thank you.
Okay. Now, would you want to do this if all you had at your disposal was like low order linear finite elements? What do you think?
No.
Probably not, right? So these methods that I'm presenting are built for higher order smooth splines. So the reason we're making this trade-off between the simplicity of constructing our flex domain, we're basically trading out the complexity of our CAD domain for a simpler flex domain. But because there's no free lunch, you engender a penalty, an error, because you no longer capture boundaries exactly. But using higher order splines, that error remains so small that from an engineering perspective, you're still far better off than you would be if you used body fitted traditional finite elements. So that's the game we're playing. That's the game you play with splines here, right? The whole point, one of the big points of this whole exercise is to try and overcome the challenges associated with building models, because that is the big issue in the industrial application of finite elements, is building the models. That's where most of the expense is incurred. And so we're using splines to directly address that issue right from the outset in terms of the formulating of the methods.
Hey, Mike, when you make those conclusions about how splines are better, I'm noticing in the equations that you wrote down, you're taking a derivative with respect to your basis function NA. And when we're talking about continuity, is that kind of where you're, basing some of your conclusions off of the how valuable splines are? Is it like, oh, there's a derivative in our equation, therefore we need smoothness, which splines capture? Is that where you're?
Well, even if you had linear finite elements and you took a derivative, these are still L2 functions, right? So you can still integrate them. If you have higher order splines, though, these derivatives are then still higher order smooth splines. And because of that, these quantities still will converge at a high rate, even the integral, like the derivative quantities. So you get optimal rates in L2 and H1 and so on, depending on your smoothness. So what's nice about splines is that your stresses are going to converge at a high rate as well, not just your displacement terms. That's nice.
So I have a question. I assume that you have the option of either using this fictitious domain approach or not with spline approaches, right?
Yeah, and in fact, you notice the way that I formulated this problem is that the only requirement is that omega c needs to be contained in omega f, which means that omega c can also be equal to omega f, right? So, or you could have like one boundary, like let me erase this, and let me erase part of this. Let me give you an example here. Like consider a classic problem like the plate with a hole. So this classic problem where you've got then a traction up here. You have symmetry here, and then you're looking for the stress singularities that pop out at the corners. With the method I'm proposing, you could go ahead and build, like if this is your radius, so here's your radius R, you could go ahead and build a spline that looks like that. Right, so this omega C, maybe I should change colors. So omega C is this blue domain. It's the plate with the hole, right? But we're solving the problem over an exact cylinder. That's our omega F. And the point is that notice that this boundary here is the same between, omega C is contained in omega F, but in fact, you're capturing this boundary that you care about, you're actually capturing it exactly in this method.
So is there any advantage to doing that over just making omega F be a square that contains everything?
Yeah, there's a huge advantage, like a huge advantage. And maybe I'll put together some results. We're working on some results to add to the lecture notes, where if you can create your flex domain so that it mimics kind of the bulk geometric parametrization of the problem, you get the same with higher order splines. You're almost very close to being as accurate as building a body fitted mesh, with dramatically less effort in building the computational model.
Yeah. So I guess what I'm getting at is that there is going to be some error introduced if your fictitious domain mesh doesn't doesn't conform to the boundaries of your body, right?
That's correct. Yep.
Okay. And so you showed that integral, so do you do anything special to integrate these discontinuous functions that arise from these boundaries?
We have special quadrature schemes that we use because the functions are nearly discontinuous depending on the value of epsilon. So yeah, but if you have a sufficient quadrature scheme, these methods, in some sense, they for a smooth problem over omega C, they converge optimally, which is surprising. Okay. And the reason is because as these functions, like if you look at this derivative term, right? Like as it goes from the CAD domain into this fictitious or flex domain, it's actually its extension into the flex domain remains a smooth function. And so it doesn't disrupt the behavior on the boundaries, does not disrupt the convergence rates. And that was a big deal when this was discovered a few years ago.
Yeah, I guess what I was wondering is if there's something special about the splines that makes that discontinuous integral easier, but it sounds like there isn't.
No, there is, absolutely. The splines are the higher order smooth splines make it so that the higher order smoothness essentially eliminates the penalty that you pay as you go up in smoothness and degree. That error that you incur for a given number of degrees of freedom gets smaller and smaller and smaller. And so again, there's no free lunch. So you incur an error by picking omega F to be whatever it is, but you can, in some sense, control that error numerically, right? It's not in the model building. You're pushing it over into the numerical methods, and then you're leveraging the behavior of splines to minimize the impact that it has on the solution.
And Dr. Scott, a point too is that even when we do body fitted meshes with, you know, traditional like linear finite elements, or, you know, it's like
Yep.
linear hexes or linear quads, even then we're still approximating the actual surface with a bunch of piecewise
Yep.
linear functions, right?
Yep.
And so even there, there's error that you're incurring in your problem.
Yeah.
Right.
Yeah. So, I mean, what you see here is that when you build these methods, like this is a good example down here on the left where you're saying, okay, well, maybe I'm really interested in this boundary here. So let me build a flex domain that, you know, oh, we don't really care about up here. We'll be able to capture these nice smooth tractions easily. And then here, maybe we want it to match. The point is that we can, in this flex method, it incorporates the whole continuum of methods, right? From what we call body fitted on one end of the spectrum all the way through to just immersion in rectilinear grids. But normally where we end up is somewhere in the continuum, right? Because you still want to build a model that is you know, appropriate, but you want it to be easy to build. And so that's the trade-off that you make here. And because yeah, go ahead.
I was going to ask, how do you handle boundaries between two materials?
Well, you just put them, the way that we do it is, let me, is this. Yeah, so the way that we do like contact and material discontinuities and all this kind of stuff is you have like one domain, here's one domain, and maybe here's another domain. They actually each are in their own omega F. So here's omega F1, here's omega F2, and then normally what we would do is we would discretize this with some kind of a Lagrange multiplier space along that boundary. That's one way to do it. That's the most generic or general way to handle those kinds of multi-body problems. You can also just do it the traditional way. So if you have a domain with two materials, you're welcome to just, you know, maybe your flex domain comes in and then matches and then goes out, comes in, matches, right? And then you're just traditional. You just use traditional techniques where you'll just introduce a discontinuity in the basis in the flex domain along here. That's another way to do it. In other words, everything you've ever done before is part of these methods as well. But it gives you, what's happening is we're beginning to formulate methods that are taking into account the fact that we're in this discretization scheme that is far more has far better resolution properties than what you do with low order finite elements. So you kind of pick whatever you want. I mean, you can do it the old way, you can do it a new way, whatever you kind of want to do. It's up to you. Okay.
Just really quick, so your omega in your left example there, you have your omega F1, your omega F2, and then inside you have your omega C1, your omega C2. Would omega C1 reside in omega F1 and omega F2? Or would
Yeah, it does, but it doesn't care about omega F2. So here's omega C1, here's omega C2. It does, in fact, in the physical coordinates, it overlaps both of these, but from the standpoint of the where we develop the discretization, you don't care about that. The only place you care about the overlap is along this boundary here. So this is nothing more. I mean, think about, let's see.
And Dr. Scott, when you finish with this, if you're interested, I've got a few slides that I could share that with the cantilever beam problem, as well as
Oh, good.
some of the
You
flex
have that, Greg?
some of the flex concepts. Yep.
Since these questions have come up right away, we might as well. Let me unshare here or stop sharing on my side. Go ahead, Greg.
Okay. So can you see my screen?
Yeah, I can see it.
Yeah.
Okay. So I'll just talk just what these results were, which are still, they're fairly preliminary, but just the idea, if we look at the, from top down, is traditional immerse schemes where effectively you're just using a simple rectilinear grid and only a few surfaces are actually tracked. And then on the right are the displacement results. And there's an exact solution to this. It should be 1 for the displacement at the tip. Anything that's in this magenta are things that are above that max solution. But so then another scheme would be to say just fit this outer boundary with this body fitted mesh, but then not worry about capturing this inner surface. And then there's a traditional body fitted spline. And effectively what you see is that fitting this one extra surface but leaving this other surface completely immersed is essentially indistinguishable. I think there's like less than 1% error, I think, between these two bottom pictures.
Yeah, it's a little bit more than 1%.
But okay.
Yeah, but the top picture had over 30% error.
Right. And that's the, if you don't really care about this, if this is just some subcomponent in a larger assembly, this may be acceptable. But if you really did care about it, then what's nice is that you don't have to go all the way to this fully body fitted representation. You can go to this intermediate representation.
And we should say, Greg, that from our perspective, all 3 of these are what we call within the flex.
Right.
They're all flex representation methods. And
Yep.
all of them under refinement converge to the same exact solution.
Right. And so this is kind of another example of like the spectrum. Some people might be familiar with this quarter piston, but the idea is that you may have all of these fillets and chamfers that are difficult or present difficulties when you're trying to build a body fitted hex mesh. And so with traditional finite cell or immersed methods, you just build one big overarching block that is completely trivial to mesh, and you don't have to worry about trying to, you just let the basis functions resolve all of these features. But then further on this scale, closer to body fitted, is that maybe we say that we want to capture the general, the biggest features of this body. So we want to capture like the bottom surface, the symmetry surfaces, the outer radius, and this top surface, but still not wanting to incur the difficulty or the pain of trying to mesh these fillets and chamfers, but we keep them in the geometry we can resolve locally if we need to. And then further is say that okay, well maybe I still want a lot of accuracy on all of these surfaces, but I really just don't want to have to try to mesh all of these little fine features. And so what you can see here is that most of these surfaces are exactly body fitted, but where there are chamfers or fillets, we're just using a little extension off and getting really close to what the geometry is. But it's kind of hard to see like the purple volume that we're meshing. That's a lot easier to mesh than having to have all those chamfers and fillets. And then traditional fine elements, what we would typically say is, I just can't afford to spend the time to mesh these chamfers and fillets, so I'm just going to remove them, and then have like the simpler volume that I'll mesh. And so, even on the traditional FEA, on the if you go all the way to the far right spectrum, we're still incurring error in our method because we've removed these fine features and made those approximations. And so that's kind of
But
the
to
whole
what-
spectrum.
To what what has been said earlier is that if you're using these other immersed methods, or whatever you're calling them, that you can increase the polynomial degree or something like that and capture those complexities. Whereas if you go to the far right, if you've removed them, you can no longer capture those no matter how much you refine the mesh.
Right. If you're here,
or
you no longer have those. You've removed them from the geometry.
Yeah,
Now,
but the other ones
right. You'll be more accurate per degree of freedom if you're, the closer you are to your actual geometry, right? So for the same amount of degrees of freedom, we would expect this method to be less accurate than this method. But again, you can adapt or resolve all of these methods to converge to the same solution. Obviously this one will converge to a different solution because it's a different geometry. But if you put the time in, which you may not be able to spend the time to build that mesh, but if you spent the time to build that body fitted hex mesh, then they would all, with all of the details, they'd all converge to the same solution, but take different amounts of degrees of freedom to get there.
Yeah, exactly.
And so this is just like just the one other example that we have that this is, again, most of this geometry is just immersed and not body fitted. But if you do care about a certain region, so say maybe you care about like the stresses in these fillets, you can do body fitted in this region, but then not have to worry about everything else.
Mm-hmm. Thanks, Greg.
Anyways, I'll stop sharing now.
No, that's helpful. Yeah, it's helpful to see that. Just take a step back.
Is that difficult to integrate both the body fitted and immersed within the same problem?
I just showed you how to do it, Lindsay. It's actually not hard at all.
Oh.
This little 1D method that we're going through has all of the features essentially that are in the full multidimensional.
Okay, it's just picking your fictitious domain.
That's right.
Okay,
yep.
I see.
Yep, that's right. And then we build our solvers are completely agnostic. They can work on any method, whether it's body fitted or not. And you'll just engender whatever errors are expected along that continuum of methods. And but the point is that, like, we're trying to replace human time with computational methods, right? Like, engineers don't want spend months building models. We would rather leverage the properties of splines to automate the back end of that problem, where we remove the human interaction and instead control accuracy through method development. And splines open the door to allowing us to do that. Okay, I think we'll stop there. I can hang around for a few minutes. Chris and Kaylin, if you guys could also hang on at the very end, that would be great. Open to other questions. Let the official lecture's over, but I'd be happy to answer any more of these.
So,
Sorry.
Dueling questions. So, in industry, we would typically characterize the easy button as just throwing a bunch of tetrahedral elements on something that is a complicated geometry. Have there been any comparisons on this immersed method with using hexahedrals in comparison to just sort of a brute force tetrahedral meshing?
Yeah, so for the same number of, like, for the same level of accuracy, I mean, we're talking multiple orders of magnitude fewer degrees of freedom for these methods.
Yeah, the answer that I would give, if I can chime in for just a second, Mike, I would say the difference is that we can pre-compute the quadrature rule that will give you the accuracy you need, and we do that once. You compute the quadrature rule that you're going to use for your problem, and then you use that same quadrature rule throughout the entire simulation. And so you have far less elements, and you still get that fine accuracy on the boundaries that end up being immersed or cut by the flex domain. So compared to like a tet mesh, which you would need, far more I mean, orders of magnitude more elements to resolve that. And every single step you have to I mean, you have to go through all those degrees of freedom, but linear solve is way bigger. And so the whole process just gets way more expensive when you have those increased degrees of freedom.
Yeah. You also, if I might chime in as well, that with tetrahedral elements, you know, if I'm doing a heat transfer problem, just like, you know, steady state heat transfer, and it's just linear, I mean, honestly, I'll probably just throw linear tets at it because I know that those are sufficient for that problem. And it is like the easy button. Where tetrahedral elements start to really suffer are on nonlinear problems, due to the just generally the quality of your mesh with tetrahedral elements will almost always be less than you'll get with hexahedral elements. And so they're more prone to robustness issues with element inversion, especially once you talk quadratic tetrahedrals for structural mechanics. They're conditioned. So because they have poor quality and you have more of them, you have poorly conditioned linear systems. They take longer to solve. Your Newton methods are based on doing a lot of linear solves. And so they just tend to be brittle when you go that approach for nonlinear problems. And so I think that's really, I think, a lot of the value behind these flex methods is that they're robust for these nonlinear problems.
And also a lot of our customers, Clint, they want CAD to be like the master, and they want methods. They're moving away from this meshing idea where you're changing the geometry or defeaturing, and they want a way for a designer to update the CAD and then immediately compute a solution. And the meshing process should be basically invisible. And defeaturing is not acceptable. This is especially true with our automotive customers. They simply do not want to remove any features anymore because they can't get the accuracy that they need to understand their engineering designs. Okay. So this method essentially allows you to never defeature anything, right? The CAD is, you don't mid-surface, you don't need to, we can do beams and shells, we know a lot about that, but I'm not even sure that that's going to be necessary anymore, frankly.
Okay. Yeah, we've had the sort of the same experience with one of our customers demanding we analyze one of our products with fully featured. And I think the only really, because of the geometry of the components, it sort of necessitated the brute force tetrahedral element approach. And it took us, in some cases, three to five iterations of convergence checks to get a converged solution, which can be a painful process. So if this is so certainly I'm excited about the prospects of this.
Yeah, so that's where in the whole field of isogeometric method, I mean, this is where the field is going. We're not kind of off in a corner doing this. This is kind of the way, this is how the field has evolved. These are the realizations that have been the things that have been learned, is that this idea of body fitting with smooth splines is not really a very relevant question anymore. It just changes that the nature of those methods are just very different than what we're used to.
Right,
just in terms of like 10,000 foot view, just kind of planning out future technology and how using it in the industry. How far out do you feel these isogeometric strategies that you're kind of showing here are going to be able to be implemented fully into FEA code commercialized?
Well, we're going to release our first commercial version of it in early spring next year. So, and that will be explicit, implicit, nonlinear contact, nonlinear materials. It's going to be fully integrated with Qubit and all kinds of CAD formats. So there will be a period, of course, of growth, but
yeah,
there's not really anything standing in the way at this point, from at least my vantage point.
Yeah, it feels like it's more about tooling at this point.
Yeah.
There's actually a really good, maybe Dr. Scott, if you wanted to add it to the references, there's a really good review paper on the finite cell method between there's like the B-splines versus traditional PFEM based finite cell.
Yeah, yeah,
That might be a good one to add to the references.
I agree. Why don't you do that, Greg?
Sure.
You've got it handy.
So we were talking at one of the lectures about isogeometric, and I don't remember all the terminology, forgive that, but you were talking about how CAD systems, you know, they're currently not using things that are really isogeometric, they're isoparametric, and that if they used isogeometric, then it would make it more simpler to do the meshing, or, you know, these methods that you're showing here with splines, they'd be more integrated with each other. Is there a CAD program that you're leveraging to be able to do that?
Well, what this shows is actually we're moving in the opposite direction, Eric. We're starting to now completely decouple the CAD representation from the method. So what that means is
Who
really
cares what the CAD's doing?
the only question the CAD kernel needs to answer is this indicator function, which is just an inside-outside test.
Okay.
And one of the reasons we're doing this is because, like, one of the things we're working on right now is integrating with some new implicit CAD kernels that are coming out of the lattice structuring and the additive manufacturing community, where they're totally redefining CAD, and it's not BREPs, it's just a totally different thing. And
Yeah.
this method could be used with that just as easily as it can with traditional CAD.
Yeah, because then you could easily say, you know, you could actually give it the lattice structure without having to mesh it.
No, that's
Isn't it even
correct. And
easier with? Sorry.
Go ahead, Ryan.
I was just going to say, isn't it even easier with implicit surfaces because it's so easy to
Well, that's
evaluate
what yeah, I mean, this maybe we're giving away too much, but we're actually starting to think that implicit CAD is in some sense optimal for finite elements, because, like, think about contact, right? I mean, intersections in implicit land are much easier than in parametric land, and inside outside is trivial for implicit. And I mean, there's a lot of powerful things that have never even been thought of because finite elements are so tied to the CAD representation. Whereas this method decouples them completely and allows us to work on any CAD, and then we can take advantage of those unique properties as they come up. But so I guess what I would say, Eric, is that we're actually, I would say, returning to the roots of IGA, where the whole point of the original work was to try and decouple and make it easier to build models from CAD, right? So that you don't have this tight coupling that complicates everything.
Right.
So we've kind of come full circle in a way, and we can capture the exact CAD, but we can do it in such a way that it's agnostic to the underlying mathematical representation, which is appropriate, especially right now where there's a lot of new ways of thinking about CAD that are coming online. Yeah. Okay, anything else? Great discussion today. All right, let's end here. Chris and Kaylin, can you guys just hang on the line?